And we are going to do neural architecture search. We are going to go back to reinforcement learning and study in detail what was the cost that a neural architecture search would take. You are going to need to have 450 GPUs, and you're going to need to use them for around 3 to 4 days. And that's going to end up being 32,400 GPU hours. If you multiply this number to that number, convert it to hours, and you want to do the same thing with only one GPU, this is how much time it's going to take you. I guess it's around 3 years or so. We need to do the math, but that's how much time it's going to take you. Okay. Is there a way to make it more manageable and more efficient? Maybe perhaps do it in 16 GPU hours. Maybe use one GPU for 16 hours, and this is going to be thousands of times faster. So this you can do at home. Let's see. What is the bottleneck with neural architecture search? You have a controller, which is an RNN. It's going to keep proposing architectures, but then to be able to adjust your controller, you need to know how good the model that's coming out of your controller is. So you have to train it until convergence. So each time that the controller is proposing a model, you have to train it until it converges. Then you're going to look at your validation data, measure the performance, and that's going to give you your reward that you can use to update the parameters of your controller. What if there is a way to don't start training from scratch? Don't start from random weights and biases. At the same time, don't wait up until convergence. And that's the idea of efficient neural architecture search. The idea is beautiful and elegant. Rather than throwing away your weights, the ones that you trained, just keep them in memory. Don't start from scratch. And all of your child models are going to share their weights. And that's the idea of weight sharing coming to the rescue again. So don't start training from scratch and don't train up until convergence. And then you're going to be able to save a lot of time. That's the big picture. Let's go into a little bit more details, like the architecture that you had for NASNet. We are going to use the same thing here. So that's the microstructure. You have some regular cells that are convolutional. You have some other reduction cells that are going to reduce the resolution. And then in terms of the microstructure, they're going to look like this. You have two previous nodes, two previous layers. You do separable convolution, identity, add them together, push the results through another node, and then keep going. You still have your recurrent neural network proposing which previous hidden states to look at and what operations to do on them. And then you're going to have different blocks. Okay, so far, so good. But what is the idea here? For node 3, you have the option to use separable convolutions that are 5 by 5. You have the option to use convolutions that are 3 by 3. You have max pooling or any other choices that you have. Some of them are parameterized, some of them are not parameterized, but keep them. Keep the weights and biases in memory. And whenever it is their turn to be used, just turn them on just recall them from the memory and do a couple of iterations on them. So that's the idea. That's how you're going to force your child models to share weights. And as I mentioned, you have the controller RNN still. It's going to tell you, it's going to make these decisions for you. What are the two previous nodes that you want to take as input? For instance, node 3 is now looking at node 2 and node 2. Node 4 is looking at node 3 and node 1. So these are the decisions that your RNN is going to make, and then what operations you're going to do. Okay, now what are the parameters? Let's set theta to be the parameters of your controller. So these are the parameters of your RNN or LSTM. And then you're going to have some parameters that are shared between every single children in your architectures. So you're going to be saving your children and their corresponding weights, and let's call them W. And these W's are shared from one model to the next model. What are you going to do? First, you're going to fix your controller. So fix theta. So you're going to be able to sample models from your controller. Maybe in this case, we're going to sample only one model. So you sample only one model from your controller, and then you're going to write down your loss function because the loss function you need it to train. And then you need the gradient of your loss function with respect to the parameters of the architectures, with respect to these omegas. And then you're going to do one step of training. You don't train too much. Maybe you train for a couple of iterations. And this way, you're adjusting the parameters of your children. But at the same time, you need to adjust the parameters of your controller. So the catch here is that you are not training up until the end. And these W's are not starting from random. They're starting with some values. Now it's your time to look at your performance metric. And then in this case, it's going to be accuracy. You want to maximize your reward. Now you're going to fix your W. You're going to fix your architectures. You're going to fix the parameters of your models. And then you're going to do reinforcement learning here to adjust your probability distribution, the one that you're using to generate models out of your recurrent neural network or your LSTM. And then you're going to do one step of that, one step of this, one step of that, one step of this. And whenever an architecture needs a convolution here, rather than a separable convolution, you just put the separable convolution in memory, bring the convolution back, update its parameters, and then in the next iteration, maybe you need to bring the separable convolution back and fix the convolution. So you're going to put everything in memory. What do you gain? Let's compare to neural architecture search, NASNet. You needed to have 450 GPUs, train them for, or use them for 3 to 4 days. And in the end, you're going to end up with a model that has this many parameters. And then that was your error rate. With efficient neural architecture search, you're going to need only one GPU. You're going to train it for this many days, 0.45, half a day. You're going to need to store more parameters. And then cutout is a data augmentation technique. So whenever you have an image, you are going to cut out some portions of it. I think it's a good time for me to stop and answer questions. There's a question in the chat. So in this case, after training, we find the architecture with biggest reward. Do we retrain the best architecture so that it finds its best parameters rather than using shared parameters? So it's the same story as before. Once you find an architecture, you're going to retrain it on your data for it to give you the maximum performance. The way that you get that architecture is slightly different. And it is based on this observation that you do not have to wait for the training of each one of your children to converge. You can just do one iteration of that, the other iteration of this. And there is a good question in the chat. Is the parameters columns talking about memory storage or number of parameters in the model? I think it is the number of parameters that your final model is going to come up with. To be honest, there is no free lunch. And can somebody tell me what is the catch here? Yes, you are training much faster, but what is the catch? Based on this observation that there is no free lunch, and it has to do with the question in the chat. It has to do with memory. Exactly. So you have to keep all of those weights in memory. What you're doing here is you're sacrificing speed, or you're sacrificing memory for speed. Now, all of these weights, for instance, for node 3, you have to keep your separable convolution and your convolution in memory while you're searching for your architecture. So maybe if you want to try this at home, that depends on the type of GPU that you have. If your GPU doesn't have enough memory to save all of these convolutions and these weights and biases, then you're going to run out of memory. Okay? And then you need to start to be smart about it. Maybe you're going to write those weights and biases on your hard drive. You don't keep them in your RAM, and then you're just going to recall them from your hard drive whenever you need them. Okay? Any other questions? So if you want to do this at home, you should be able to do it, unlike the previous ones. Okay?